Good morning, everybody. Welcome, welcome. Last Friday was the campus Halloween day. There was a big community Halloween thing in the evening, bring all the kiddies and all that kind of stuff. And so the Science and Engineering Club was dressing up, and one of my former students dressed up and said that he picked the scariest costume that he could possibly imagine. Right? What's that? Yeah, his you can't read it, but his name tag says Mr. Balogh on it. I don't wear this hat for you guys. This is a Physics 4 thing where I really torture them with vectors, and so I call that my vector hat. And so he got a vector hat. He got a lab coat. I mean, he made Mr. Balogh look good, right? I took him to my boss and said you should hire him for me, and we'll all be good. I know, though that was the shocking thing, right? Like everybody was talking about the shoes, and that was totally an accident, right? And I just happened on Friday to be wearing my lab coat and my sweats, right? But he had a polo and slacks. He made it look good. He made it look good. So there you go. And I apologize. His name's Josh. I apologize to Josh profusely for the effect that costume would have on his social life, right? It's not good. It's not good. But yeah, I've already had a few of you in this class accuse me of being nightmare fuel for that school dream where the teacher is giving you a test and you haven't studied for it and all that kind of stuff. I don't know if you've had those kinds of dreams yet, but now you will. Yeah. So. I won't apologize, right? It is what it is, and the dreams continue for the rest of your life. It's just something that college does to you. And for me, the dreams have switched from being a student in the class to being a teacher in the class. And I come in, and either I'm not ready to lecture, everybody's looking at me like I'm supposed to know what I'm doing, or the worst one is I walk in to give an exam and I haven't written the exam. And all of the students are looking at me, right? Where's our exam, Mr. Balogh? I'm like, I don't. We are in chapter 27 still. Yeah, the never-ending 27. Because A, I talk about it too much, and B, there's just a lot of stuff in the chapter. So diffraction. This is kind of the last major thing that we need to cover. We've done reflection and refraction. And the law of reflection led us to mirrors. Refraction led us to lenses. And then this chapter has been on interference so far. We did double slit interference, and we did thin film interference. And then now we're finally getting to the diffraction. Remember, diffraction and interference are the two things that only waves can do, right? Particles cannot do thin film interference. They can't do double slits. And they can't do this thing called diffraction. So what I want to do is I want to show you several videos of sort of what diffraction is, how it's different from interference. But spoiler alert, it's going to feel a lot like interference. Like the patterns are going to look very similar and all that kind of stuff. The difference lies in the fact that with diffraction, this is the bending of light either through an opening or around an obstacle, whereas interference is all about how the light waves superimpose themselves.
We'll use this ripple paint, which projects an image of waves on the surface of water, to show diffraction through a single slit.
Oh.
If we put a single slit in front of the waves emerging from the slit are no longer plane.
Do you see how they bend out?
Waves are now diffracted.
That's diffraction. They were flat, but when they go through the opening, they spread out.
Diffraction is reduced.
This
split screen view shows the diffraction at
the size of the opening will affect, right, the amount of diffraction that you get.
Also decreases the diffraction of the waves.
Yeah, you're right.
This split screen view shows the diffraction with two different slit widths.
The width like the size of the opening. When we did interference, it was the distance between the two slits. But with diffraction, it's how big the opening is.
We'll shine the beam from this laser through a slit whose width can be varied by turning a screw. Here is the laser spot on the screen when the slit is opened wider than the beam.
Very big, wide open
We'll
slit.
close the slit down part way. The laser spot now appears to spread out slightly. As we continue to narrow the slit, a pattern of bright and dark spots appears on the screen.
Looks like an interference pattern, doesn't it? It's not. It's a diffraction pattern.
When the slit is almost closed, the pattern spreads out so far it nearly disappears. As the slit is opened again, the spot narrows, and the pattern of bright and dark spots reappears.
So obviously there's something going on with this like width of the slit, right? And the amount of diffraction that you'll have. If the slit is really, really like big, okay, compared to the wavelength of the wave that's going through it, then you don't get hardly any diffraction at all. They showed that laser beam just being a bright dot, right? But as they clamped down on it and they got the width smaller and smaller and smaller, then we got to see more and more diffraction. So anything that's a wave will do this, right? And the diffraction pattern can happen either going through an opening or around an object, like a very thin wire.
Light passing a thin wire is diffracted.
I said that
We'll
already.
use a thin wire and a laser to show the pattern of bright and dark spots caused by the diffraction. Here is the setup of laser, wire, and screen. This is the laser spot on the screen with no wire in the beam. This is the diffraction pattern obtained on the screen when the wire is inserted.
So that wasn't going like through an opening, it was trying to go around something, right? But the diffraction pattern stayed the same. Bright central, bright things, pattern of dark and brights going after it. And then here is Monsieur Poisson.
Although light has properties similar to those of waves, the wavelength of light is so small that we seldom notice the wave-like nature of light. This pinpoint light source will allow us to demonstrate that wave-like nature. If we put the light source behind a small sphere and look at the light coming past the sphere, we see a pattern around the edges caused by interference between different waves of light. Notice the bright spot in the center of the
It's really, you can't see it on this
Normally
screen.
expect no light at all.
There is a bright spot there. I got a better picture of it. On my screen with the video recording, it was there. I didn't realize these screens were not contrasty enough to see it. So let me show you what that actually looks like. So the reason I think like Newton didn't like see a diffraction pattern, didn't see interference, he was limited by sort of the equipment of his day, and they couldn't look really closely at like the edges of things and shadows that were happening. The diffraction pattern is there. It just can be very difficult to see if you don't have like monochromatic or single color light and all that sort of stuff. So if you shine like a laser and it hits the edge of an object, if you zoom in on that shadow, you'll actually see this diffraction pattern starting. And here's what that Poisson spot looks like. What you're seeing here is a circular diffraction pattern because the light's going around that metal ball that's sitting in the middle of the light. But that bright spot right there in the middle of that shadow, if light was a particle, shouldn't exist, right? And again, we call that Poisson spot because he's the one, even though he believed it wasn't going to be there, he's the one that described it correctly. The diffraction pattern, you can look at it, I've got an example of the pattern on the screen. Again, looks a lot like an interference pattern. And I will never like ask you which one of these is interference, which one of them is diffraction. That's getting into the weeds just a little bit too much. But a diffraction pattern has a giveaway central maximum that tends to be a lot bigger than an interference pattern. And so that's one of the ways. That and I know this slide might not mean too much to you, but as far as the intensity of the pattern is concerned, in diffraction, the central maximum is very bright, very intense. And then the subsequent maxima, as you go to like 1, 2, 3, and 4, and you keep counting out sideways, they like die off really quick in a diffraction pattern. In an interference pattern, the central bright is bright, but the ones on the side, they do fall off also, but they fall off like much more gradually. So again, these are very detailed things I wouldn't expect you to know, and it's confusing. I get it. It's really confusing because a diffraction pattern looks like an interference pattern. And as we move on to diffraction gratings, it'll get even worse. Okay, let's not do that calculation because I'm not making you do that on your homework or on your exam. So let's talk instead about diffraction gratings, because this is where you're going to run into diffraction on a professional basis. Because if you go into any kind of technical field, you'll probably end up either getting data from or actually using a device called a spectroscoper. This is something that can split up information into its basic parts. In the case of spectroscopy for light, we can split like sunlight into its various colors, or if we had a sample that we were trying to determine what it consisted of, we can figure out what the individual parts of the sample are going to be. And so I brought a demonstration today, and you're going to need your groovy glasses. I call them groovy glasses because not only do they make you look groovy, if you put them on, go ahead and grab one at your table, right? If you put them on and look at some of the lights, I mean, like, yeah, seriously, who needs drugs when you have physics? Right? Like look at kind of a light across. Do you see the rainbow patterns that are there? Right? So what we're going to do with these groovy glasses, and these are kind of cheap party trick glasses. A true diffraction grating is actually a very expensive thing and can be very precise in how it spreads out the light. And usually only has a single axis of diffraction. Your groovy glasses here have 2 axes, so you're getting the rainbow pattern all the way around the lights. But let's turn off all the lights in the room. Let's see if we can really get it to be dark enough in here. I'm not terribly hopeful, but we'll see. Mute. That's not mute, that's blue. I know, look at the blue. Whoa. I want you to go off. I don't want you to just go blue. We're going to go dangerous here. We'll see how long it takes us to turn back on when we finally get there. Okay, what are we seeing right now? We're seeing like the white light from the open doors, right? I really hope I don't have to put the curtains up. But do you see the white light coming through, and it's got that rainbow coming through there, right? What I want to do, where did it go? Let's see if this one works a little bit better. I might have to put up the curtains. We'll see. It's the first time I'm trying this demonstration in this room, so I'm experimenting. You are my guinea pigs. Okay, let's see. If I hold this light up, can you guys see if I hold it like this, can everybody see the rainbow? Yeah. You see like repetitions of the pattern, right? There's the main thing at the center, and then there's a set of rainbows around that, and then another set of rainbows outside that. What you're seeing in the language of diffraction patterns is orders of the pattern. So m equals 0 is the actual light. M equals 1 is the first set of rainbows that you see. M equals 2 is the third set, right? So on and so forth, going out. And they get fainter and fainter as they go out. What they are repetitions of the pattern, okay? So this is a this is a incandescent light bulb, so it shows you all the colors of the rainbow. And what I want you to look at now is this device I have here. I'm just going to have to kind of individually show this to different parts of the room. If you look through the groovy glasses, do you see not a full rainbow? Is it dark enough in here to see the pattern okay? I haven't looked at it yet. Yeah, you should see. I need to test it out here. Oh yeah, I can see it, right? There's a little bit of like bleed from my computer monitor and stuff like that. Just kind of ignore those rainbows. But you should see the individual colors that make up this electrified gas. Okay? Now, if you take the groovy glasses off, right? If you look at that gas, can everybody see that from no matter what angle? You see that okay? All right, so take the glasses off, you see the orangish color, right? But if you put the glasses back on, you start to see the colors that make up that orange. This is the fingerprint. It's the spectral fingerprint of this gas, and the gas you are looking at is neon gas. So like a neon sign, okay? Neon signs don't look this color. They look like all different colors. And the different colors of a neon sign exist because they've electrified different gases. So it's not all neon, because neon, being the noble gas it is, this is it. It only gives one color because it only has one fingerprint. Okay? So if I go ahead and switch out the neon, I did almost shock myself on this thing this morning, so I'm being extra careful. It had switched on without me realizing it. And I went in to grab the tube, and the tube started glowing before it was plugged in. I was like, whoa! Good thing the one-handed rule was in operation. This power supply is about 10,000 volts, so gotta be careful. All right. I don't know if this is going to be bright enough for you guys to see the pattern. This is the one I was worried about. Okay, I can see it. I'm this far away. It looks like it consists of a really bright, like reddish line, and then a blue, like on the other side, like almost like a cyan. And if we could get the drapes up and kill the light in here, we could probably see there's a little bit of a yellow line in there. Okay, there's a bit of bleed coming from the other lights in the room. But this is the most studied gas in all of human culture and scientific literature and all that kind of stuff. Does anybody want to guess what it is? Hydrogen, right? Okay. You're looking at the fingerprint for hydrogen, right? And that fingerprint tells us it's hydrogen. And this is one way that astronomers, I'm going to turn the lights back on right now so it's going to be bright. That fingerprint is what allows astronomers to say, hey, we know that that star has hydrogen in it, right? They can point their telescopes at the star, read its spectral, right, lines through this thing I'm about to teach you, the diffraction grating. Okay, you just get a much better version than the one we have in our plastic glasses there, right? And then they can say, oh, we see the fingerprint of hydrogen. We see the fingerprint of helium. We see the fingerprint of oxygen and carbon. Like every element on the periodic table has its own fingerprint or set of spectral lines. And diffraction gratings is the way that we use to take the light from that star or take the light from that gas or take the light from that substance and break it down into its individual frequencies and individual wavelengths. When we move into quantum mechanics and we start talking about chemistry and applications of quantum mechanics, we'll circle back to this and we'll start talking about how electrons transition in their orbitals. And some of you, I can already see your eyes glazing over as I start mentioning words like that because you had chemistry, right? And we'll talk about where these lines come from. What we're doing today is we're talking about the physics of how the diffraction grating is able to separate out all of these things. So what do I want to do? I know you can't see anything yet. We'll start here and then go. We're going to go that one and that one. Let's see if it works. Let's see if it works. Okay. I'm just going to drop the equation on you so you have it, and then we'll talk about its implications, okay? This is how your book writes it, and I'm actually kind of a fan because this equation, have you seen this equation before? Yeah, right? Because if you just move the d back to where it should be, right? D sine theta equals m lambda, what is this? This is double slit interference equation, right? Yeah, this is the part that it drives people nuts. The equations for the diffraction grating and the equations for double slit interference are the same equations. Key differences. In diffraction gratings, we don't do the m plus half equation. We only need this equation, and it's not the constructive equation. In diffraction, we have bright and dark spots, but we don't use the terms constructive and destructive interference because we are trying. This is a unique, different phenomenon from interference, even though interference is involved and there's some patterns there. So I actually kind of like how your book writes the equation this way to kind of trick your brain a little bit into, okay, this is different. It's the same exact equation. It's the same exact geometry even, right? Okay, because instead of just two slits next to each other, there's lots of slits next to each other. That's what these glasses are. The plastic in these glasses has a bunch of rulings in it or little tiny grooves in it, and they did them both ways, right? Okay, and that's what is giving rise to this pattern. So in the diffraction grating, right, if you just look at two slits next to each other, now you've got double slit interference, right? The problem is we got to build up this phenomenon from an infinite number of double slits, right, to give rise to the pattern that we see. What we do in the equation is this m value right here, this counts the orders of the pattern. An order is a complete pattern replicated several times. And I'll show you some pictures of what that means. But back in the double slit, m was counting, it was like an integer, right? 1, 2, 3, 4, 5. M is still an integer, but it's order number 1, order number 2, order number 3, okay? And I'm not talking about, Big Mac fries and a drink. Talking about replications of the pattern as they come across. This little d right here, you'll see words like ruling or that's a little bit misleading. What did I write down for you guys for this? It's here somewhere. Not there, right there. What did I do with it? You'll see I didn't write it down. You'll see words like rulings, okay, or the ruling of the grating. The rulings will give you, it'll be like lines per centimeter is a very typical way that they will tell you about a diffraction grating. It's the number of these openings or spacings, right, per centimeter, which of course is an awkward unit because you really need to get it into meters anyway. So make sure to convert. But d is the distance between individual slits, right? So d is a distance, right? But rulings is the number of lines per centimeter, and the rulings is like the inverse of that distance, right? So if you know the ruling of your diffraction grating and you invert that number, you will get the distance between lines in your diffraction grating. What does all that mean? Okay. So this is a picture of the, like when I'm trying to talk about the orders. Okay. And you saw this just a little bit through your groovy glasses, right? You can even put them on now and just look at the regular lights in the room to see this, right? There was this, you saw like kind of you see the light and then you see the first set of rainbows. That's the first order pattern, okay? But then that pattern repeats itself again and again, and unfortunately they kind of start overlapping out here. Generally, we're trying to find like the first order pattern and just deal with that one, but the other order patterns can do it. This is a DVD or a CD, right? So you don't have to have like something that light can pass through, like the groovy glasses you have here. Diffraction, you can have a reflective grating, which basically is a piece of glass or plastic that has grooves cut into the surface. And as the light comes in and bounces off, you get diffraction happening as well. I know that, again, sounds like reflection, but it's not. It's diffraction. And the reason that you're seeing a whole bunch of pretty colors in the disc here is because the disc has all those little grooves cut into it. If the white light shines on it, you can see it splitting up in there. So what typically happens when you're dealing with diffraction is you're measuring an angle. You're looking like you're using a telescope, actually. Not a microscope, believe it or not. But you're using this thing to lock on to a certain order that you're peering at, okay? It's coming from a source and there's diffraction and all this kind of stuff's happening, right? You got your diffraction grating right here. But this angle gets measured. And in our equation, we'll get there in a second, there's our angle. That is not a small angle. So unlike like in interference and all that kind of stuff, we kept saying, small angle approximation, you don't need to worry about it, just make it y over, don't worry about the trig function. Here we have to worry about the trig function, like because the angles you measure are 20, 30, 40, 50 degrees, okay? And so it is a problem. The equation itself is not hard, right? It's sussing together all the different parts of it and making sure you're understanding exactly what's going on. So let's do an example problem of that. Oh, by the way, here's another example. Here's the central max. This is m equals 0. This is what the light actually looks like as it comes into your eye. And then here's the first order. Kylo Ren's going to come right after you. Okay? So it's replicated on either side of the central. Okay? And it's a full pattern, right? And then the pattern is replicated again, right? So that would be the second order, or m equals 2 pattern, and so on and so forth as you go out in angles spread across. So that's what it would actually look like through a decent spectrometer grating, not our groovy glasses, which are sort of a fun party trick. So let's do an example of working with a diffraction grating so that we can figure out how to apply our equations and sort of what they mean and all of that kind of stuff. Where is my notes for this one? I don't have, no. I have a feeling some pages fell out of my notebook. Nope. All right, well, let's have fun. We're going to need some calculators to be able to pull this one off. Okay, what do we know? Well, it's a diffraction grating problem, and so operative equations are sine theta equals m lambda over d, and that's basically kind of all we got, okay? So wavelength, we know that, they gave it to us, right? 580 nanometers. And what can we tell about our m value, as in Mike? What does that say right there? Fifth order. So what are we going to put in for m? 5. That's not so bad. So you got to be able to read, right? And they gave me the angle, of 32 degrees. Okay? So part A, what is the density of rulings for the grating? Again, they did not ask for D. We're going to find D to help us get this density of rulings. But this density of rulings that they're talking about here, okay, that's the number of lines or rulings or gratings per distance. Okay? Lines per meter, lines per centimeter, lines per light year. As long as you use the units, you'll be all right. Okay? But if I put standard units in, I should get standard units out, meaning that if I solve the equation for D and I find that the distance between rulings is 10 centimeters, right? It's not, okay? Then I could invert that to find the density. So that's what we're going to do. We're going to use sine theta equals m lambda over D, solve this for D, and see where it gets us. So this is 5 times, okay, what am I going to put in for the wavelength? 580 times 10 to the minus 9, right? Because now, I mean, I could leave it as 580 nanometers and my answer would come out in nanometers, but now then I have to go get a density of rulings and my units are just going to start getting screwed up. So I'm just going to go straight to standard units all over sine of 32 degrees. Has anybody got this? Bet you guys are going to be faster than me because I don't use calculators. Anybody gotten it yet? Don't let me win. I won. 5.47 times 10 to the minus 6 meters. Did anybody else get? Yeah, you got it? Okay. That's 2 of us. We'll just pretend we're the smartest ones in the room. All right. So, not that the actual number matters as much as the process. So what I found there was the distance between 2 slits in the diffraction grating. Okay? They want to know how many slits there are in a certain distance. That's what the density of rulings was going to be. So this density, there isn't really any symbol for this. Sometimes little l is used, but it's not standard. Okay? The density is going to be 1 over my distance. Okay? And it's going to have units of like lines because between 2 lines, there's 5.47 times 10 to the 6 meters. So this is going to turn out lines per meter when I do this. Okay? So I'm going to do 1 over 5.47 times 10 to the minus 6, which if my calculator is still up, I should be able to hit that button, and I get 182,730 lines per meter. Okay? That would be the density of rulings. Typically, a manufacturer will do this in lines per centimeter. So how would we convert this to lines per centimeter? Yeah, you can either move the decimal place or do it this way. Lines per meter, and then for every 1 meter, there's 100 centimeters, right? So I know I've got to take this number, divide by 100, and I've got 1,827 lines per centimeter. So either one of those. And again, I think the reason that diffraction grating manufacturers do it that way, and all of the machines that use diffraction gratings will give the ruling density in lines per centimeter, is it's just a smaller number, right? I don't have to talk about 182,000. I can just say 1,827. So that's typically what goes on when you work around these things for long periods of time. All right, that was part A. Okay, so was the math hard? It really wasn't, right? And being able to identify an order number, right? They just usually tell you, or sometimes you're looking for it, right? But it gets a little bit confusing because it looks so much like interference, and the D now isn't the thing as it was in two-slit differential. So try to find a way to help your brain not get too confused about this, right? But when you're dealing with a diffraction grating, make sure that you are not using small angle approximation, and figure out what you need to solve for and go for it. We didn't do part B, right? Part B over here. Determine the total number of primary maxima. All right. What are they asking there? Okay. They're asking for the total number of orders that you could see looking at this pattern. Okay. And so what we're doing here is we're going to solve for m. Right? We want to know, like, what is the maximum value of m that you can get? And that might seem a little bit weird. You're like, well, I thought m could go all the way out to like infinity. And for double slit interference for thin films, yeah, kind of. You get to a point where there's so little light being reflected that it doesn't matter anymore. But if we take this equation and we just kind of play with it a little bit, right? And we solve it for m. Let's see, that's d sine theta all over lambda equals m. Okay? Now, we know the wavelength, and now we know the d, right? We just found it for this grating. The question, so what is m going to be limited by? Well, like our eyesight, but what angle could we put in here, right? That would represent like maximum. It's a feature of sine and cosine that is very important, and a lot of people know but don't realize the implications of. Like sine theta. What's the largest sine theta can ever be? 1, right? And if we go like past 90 degrees, because sine of 90 is 1, if we go past 90 degrees, it's going to become less than 1, right? Like the most that this equation over here can ever be, the biggest, right, that m could ever be is limited by what the sine is doing. The d and the lambda are fixed. And so if we kind of say, well, if sine of theta equals 1, right, or in other words, theta is equal to 90 degrees, then we have max, right? And so that means that we have d over lambda equals m. And we can calculate this. D, 5.47 times 10 to the minus 6 divided by the wavelength, 580 times 10 to the minus 9. Anybody got it yet? Shout out if you got it. Okay, I got 9.43. Anybody else? Yeah, okay, right? So what does this mean? M. What does m have to be? Well, okay, it can only be an integer, right? So you can't have 0.43 of something. So what's the largest value m can be in this situation? 9, okay? So we could theoretically, with this setup and this grading and this light and all that kind of stuff, we can see out to the 9th order maximum. But that's not what the question asked. What are the total number of primary maxima that can be seen? It's 9 this way and mirrored 9 the other way. What's 9 plus 9? And that's still the wrong answer. Because the answer is 19. Because of the m equals 0. Okay? It asks for the total number of primary maxima. The 0 counts as one of those. Even though it's not a rainbow pattern, right? It's still one of the primary maxima. So this is a case where the author of this problem is trying to make your life difficult, right? Part A of this problem, I'm totally behind. This is standard diffraction grating work, right? But then, because diffraction gratings apparently, again, aren't hard enough, authors of textbooks and things will try to sneak in things like this. And then you get frustrated, right? You start like, well, it's 18. And you keep putting 18 into Wiley plus, right? What's the definition of insanity? Doing the same thing over and over again, expecting a different result, right? So like, it's not taking 18. You don't understand why it's taking 18. And it's because you didn't think m equals 0 was part of the pattern, right? So we found that the maximum m could ever be for this situation was 9. And we had to realize, well, that's replicated on the other side. So that's 18 plus the m equals 0, 19. So I show that to you just so that you are not caught off guard, maybe. I do try to avoid these kind of things when I assign your homework, but I'm not always successful, as you've seen already in the course. Okay? But I've seen this trick several times where they're asking how many primary maxima are there. Well, it's whatever m is times 2 plus 1. Okay, so let's take this one step further and start talking about resolution, because diffraction limits our ability to resolve individual objects. Now, as soon as I say resolution, people tend to start thinking about like the resolution of their monitor or something like that. And this is involved, and we're going to talk about monitors and pixels and all that kind of stuff, okay? But one thing you need to understand about diffraction is that it limits the ability of light to be able to detect things. And let's see if I can do an example of this, okay? If I come over here in this doorway, okay? Now, if you can see me if I stand in the doorway, right? And you can hear me and all that kind of stuff, okay? Well, what if I do this? Can you see me? Were you able to hear me? Yeah, right? So you can hear me even though you can't see me. Why are you able to hear me through the door but not see me through the door? It has everything to do with diffraction. The wavelength of sound waves are about a meter. Some are a little bit bigger, a little bit smaller, but on average it's about a meter. And how wide is this door? It's about a meter, right? So the wavelength of sound and the opening through which that sound is propagating are about the same, which means that the sound will diffract through the door. Now, light, on the other hand, has wavelength measured in 600 nanometers, 5 or 600 billionths of a meter. This is like, we're talking about way, way smaller than the width of a human hair. Okay? And so why doesn't light diffract through the door's opening? It's like the slit might as well be infinitely large, right? The slit might as well be the size of the United States compared to us, right? Like it's so big that the light goes, well, I can't diffract. I'm not going to bend, right? I'm just sailing like through because there's no obstacles. If we go outside and we stand like on that side of the building and we listen to a car alarm going off in the parking garage, right? We can't see the parking garage. Because again, light won't diffract around the building because the building's too big compared to the wavelength of light. But the sound waves will bend over and around the building no problem. Because the building is on the order of meters, tens of meters big, and sound waves are meters big, and so it'll diffract. Microwave ovens. For some reason, I don't understand this at all. It really drives me nuts. Oven doors, like a conventional oven or a microwave oven door, what must happen for you to feel comfortable about cooking? Not just having the door closed. Anybody that's a fan of the Great British Bake Off knows exactly what I'm talking about, because what are all the bakers doing during the Bake Off when something's in the oven? Staring into the oven through the glass window. The glass window is just a place for energy to leak out. In fact, if you ever get to go to a professional kitchen, take a look at their ovens. What do their ovens not have in the door? No windows, right? Because it keeps the temperature consistent instead of having this being able to look in. You can't see it anyway. There's so much food splattered on the other side of the glass, right? It doesn't make any difference. Same thing with a microwave oven. A microwave oven is a box that puts a whole bunch of microwave energy into it, and that can cook things like any kind of flesh, including you, right? So to keep you safe, they have to put shielding. It's a big Faraday cage around there. But they couldn't sell microwave ovens because people kept complaining that they couldn't see their potato blowing up in it, right? So they figured out a way to put a window. If you look at your microwave oven's window, what does the window have in it? A metal mesh with a bunch of little tiny circles in it, right? So they're setting up a Faraday cage, but the reason the Faraday cage still works, even though there's openings in there, is that microwaves have a wavelength of about 1 or 2 centimeters. Those openings are like less than a millimeter big. So what can go through without diffracting? Light. But the microwaves, when they try to go through a really tiny hole, will diffract so much that they basically just spread out so much that their energy just dies, right? So this is called the diffraction limitation. And it affects like microscopes. Visual light microscopes can only see things that are small. We can get down to structures within a cell, but not much beyond that with visible light, because the light will just start bending around DNA molecules, right? We can't see it because we can't get any light to bounce off the DNA molecule, right? And so we have to use something else to be able to see smaller things. Again, it's called a diffraction limitation. Any aperture light detector of any kind is going to have a diffraction limitation, including your Mark I eyeballs that are installed in your head right now. Because we have a circular aperture, light's coming in, there's a size to that, and we are going to limit our ability to see things based on the size of our pupils in our iris. So I'm going to drop an equation on you and then explain how to use it, okay? It's going to look familiar again, right? Like, you know, they all seem to be kind of the same. Only it ends here, okay? 1.22 lambda, and I'm going to put a capital D here to make sure that we know that this is different. This is diameter of a circular aperture. We are going to do resolution and Rayleigh criterion. What I wrote on the screen was the Rayleigh criterion. This diameter of a circular opening. So we're not talking about slits anymore. We're doing like a two-dimensional slit is what this is, okay? A circular opening. The equation changes slightly because you'll notice there's no m, right? There's no counting number here. When you go to 2 dimensions, you do a circular aperture. You don't have like a counting number to tell you which order you're talking about. You actually have a new equation for every order. Okay, that 1.22 is a bit of a multiplier on there, but the equations actually change and look different depending on, like, if you go to the quote-unquote m equals 2 or second order pattern for a circular aperture. No, it's a totally different equation, right? So this is the first order equation for a circular aperture, and it's also known as the Rayleigh criterion. Sir Walter Rayleigh, okay, British guy's last name, discovered a phenomenon that exists for all diffraction-limited scenarios. When 2 diffraction patterns overlap from light sources that we're looking at, if they overlap such that the maximum of one diffraction pattern sits in the first minima of the other source's diffraction pattern, we lose the ability to resolve or tell the difference between the objects. Let me show you what's going on, and then we'll come back to this equation, okay? So here's an attempt at trying to show you what's happening here. If you look at the picture over here on the right, okay, First of all, we're seeing the circular diffraction pattern. It's that concentric circles. You got the central maximum and then a bright fringe and blah, 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 blah. Okay? What our equation gave us, right, the Rayleigh criterion, was the first like bright pattern around the maxima. But in this right-hand picture, the two sources are sitting right on top of each other. And so obviously if think of two light bulbs or something, right? Two laser beams, and they're sitting right on top of each other. You can't tell the difference between them, no matter how close or far away you get. But as those two sources begin to move apart from each other, your eyeball is getting some diffraction because of the smallness of the light that's coming through it. And depending on how far away things are and blah, 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 the diffraction limitation will start hitting. And in this middle picture right here, we can kind of tell that there's two patterns that are overlapping, but for our brains and for our eyes, we really can't tell the difference between those things. Our brain will see this still as a singular object. But if we get them far enough separated from each other such that our eyes see two distinct diffraction patterns, and we get outside the Rayleigh criterion, then we can tell the difference between these two things. This is called the resolution limit, and it affects telescopes, it affects eyeballs, it affects microscopes, anything that's got a circular opening, cameras, and you're trying to tell the difference between things. I'm going to give you a whole bunch of examples to hopefully try and make this fit. We're not going to do it, but if we went outside right now, we looked across the street, we would see the trees, right, that are next to Ratcliffe Stadium, right? And if we looked way over at the Sierra Nevadas, we would also see trees on the Sierra Nevadas, but we would not see individual trees, right? We'd see the green sort of darker parts that have trees on it, and then the brighter parts that are the granite, and so on and so forth. So why is it that we can see individual trees closer to us, but we can't see individual trees far away from us? The answer can no longer be, well, it's just because they're far away. Like, what? In theory, it shouldn't matter how far away things are, right? I should be able to tell the difference between them. But because of diffraction, and because of the circular openings of our eyes and anything else, we cannot see the individual trees in the Sierra Nevadas with our eyes. Now, if we went and got a big telescope and pointed it at the mountains and like zoomed us way in, would we be able to see individual trees? Yeah, because now we've overcome the diffraction limitation. We've overcome the Rayleigh criterion for that particular optical setup. This happens at night if you're driving on the road, okay? If you're ever in a situation where you can see way down the highway, pay attention to your driving. Don't be dangerous, right? Okay? But if you look down, you can see things like stretching down 99 or something like that, okay? At night. If you look way in the distance, all of the cars look like motorcycles. The two headlights, because the cars are so far away, will appear to just be a single light source, okay? And then as they get closer and as you hit the Rayleigh limit, all of a sudden, that one headlight will turn into two, okay? Unless it's truly a motorcycle, in which case it stays one light the whole time, right? Okay? But depending on how far away you get, right, the headlights will appear to be a single light. Again, this is the resolution limit. And when we say that, what we mean is the ability to resolve the difference between two objects. I gave you the equation for Rayleigh's criterion, but in practical terms, we need to talk about kind of how to use it, right? So let me redo it here. It's sine theta equals 1.22 lambda over d. This angle that is used, we are back now to the small angle approximation, because usually we're talking about like thousands to tens of thousands of meters for the L, and then like just a few meters for the separation between objects. That would be my example for looking at the mountains, right? The mountains are tens of kilometers away, but the trees are 1 or 2 meters apart from each other, right? But it can also be like we're looking at our cell phones, right? And we can't distinguish the individual pixels on the screen. The distance from our phones to our eyes is 25, 30, maybe 40 centimeters away, but the pixels are like microns apart from each other, right? So what's going on here is this L, this distance right here, is a whole lot bigger than the separation D on this. I don't know, it's too many D's in optics. I'm going to do my own thing. We're going to cross that one out. We're going to call this Y. Okay? The separation distance between objects. Okay? So here's a trick. Using the small angle approximation, remember, the angle is approximately equal to the tangent. So sine and tangent, when the angle's small enough, are about the same thing. And tangent in this case is just y over L. And some of you are going, Mr. Balogh, that doesn't work because I have to go like a right triangle, don't I? So this would be y over 2, and this would be L. And so where's your factor of 2? It doesn't matter. It's so small that a factor of 2 is not going to change anything. And so what we do is we cheat just a little bit in this derivation. And we say, you know what? The tangent's just y over L. Like, this drawing shows that there's like spread here, right? But there really isn't, okay? This angle is so tiny that distinguishing between the actual spread and the right triangle, don't bother. Okay, so a lot of times the operative equation, the one that you use to actually calculate things, doesn't involve an angle at all. Okay, it just involves y, the separation distance between things, between two objects, L, how far away the aperture, the device that's looking at it, right, is, and then D, big D, the diameter of that aperture. Okay, so the one there in the box is the one that you're actually going to want to use, like on your homework, on the test, that kind of stuff, right? Even though Rayleigh's criterion has a sine angle in it, it's so small, we don't even bother it. Sometimes problems, I think I do an example of this, will refer to the angular separation between objects, okay? That angle, right, okay, is just y over L. Like literally, don't try to calculate sine of that angle, okay? If you're being asked for the angular separation, just find y over L. And y over L is just 1.22 lambda over d, right? And the units will be in radians. Y has units of meters. L has units of meters. When you divide meters by meters, you get no unit. And so that angle would have units, the non-unit of radian. All right. So this is a picture that's showing you what happens when the diameter. So all of these objects are the same distance away from the telescope, I think in this case, that's using it, right? And so a small aperture telescope would lead us to see, let's say that these are all stars maybe. I think this is simulated, but like, let's pretend they're all stars. So like, do you see how in the small aperture, 3 and 4, they look like they're basically the same smudged out thing, right? We can tell the difference between 1 and 2 and the combo 3, 4 for the small aperture. But when we get to the medium aperture, 3 and 4 actually start to separate from each other. We can tell the difference. And then a large aperture. So why is it that we want really, really big telescopes? Like astronomers love big telescopes. The world's largest telescope has a diameter of like 34 meters. Okay? It's huge. That's optical telescope. Okay? We can do radio telescopes that have a diameter the size of the Earth. Talk about that later. Okay? So why is bigger better? It really kind of does depend on the wavelength you're using, but if we'll just talk visible light now. Why is a bigger aperture better? What happens to the resolution of the image? Does it get better or worse? It's a lot better. So if we're trying to see distant stars, we're trying to separate out those stars from the other stars that are nearby, We want high resolution, meaning that we need a really big aperture to be able to do that. This is what the surface of your flat panel monitor probably looks like. This is what the surface of your phone probably looks like. I'm lying a little bit here. I'm oversimplifying because depending on if your screen is OLED or not, or just LCD, it might be TFT, which stands for thin film transistor. Thin films, right? So there's lots of different technologies for how computer monitors and displays do their thing. But in the end, it comes down to this concept of the pixel and the subpixel. So an individual pixel on our screens consists of a red, green, and blue block. And I've tried to, it's not very clear here, but that I've isolated one of the pixels. But the subpixels are RGB, red, green, blue. And when you put red, green, and blue together for the human eye, you can get like 16 million different colors, depending on how well you can control the subpixels. So we're looking at like a single pixel is a group of 3 subpixels. Each subpixel, red, green, blue. If you turn the red, the green, and the blue all on the same intensity, what color do you get? If you get red, green, and blue, all the same intensity, what color is that? White. Okay. If you turn off all the subpixels, what do you get? Black. Okay. And then you can get all the other colors of the rainbow by messing around, right, with the different things. I can't remember what the colors are, but like if we do green and blue, I can't remember what color that is. So like a yellowish, I can't remember what they are. Cyan, something. Like you can combine these things. If you can control the subpixels to like, I think it's just 256 different levels in a subpixel, you can get like, I can't remember, I think it's 16 million different color shades. Okay, which is way beyond what like our brains can tell the difference among, right? My wife and I are planning a renovation now, and we're going through all the paint colors, and I just lost it. I was just like, you've shown me all blue, and they're all the same, right? Why is this one called ocean mist, and this one's called cow's udder, and this one's like what are these names, right? Like, so just drives me up the wall. Okay. So let's use the Rayleigh criterion, the resolution criterion, to figure out, right, like how far away from, is this question? Yeah, okay. How far away we need to be able to see the pixels on our phone screens. About 10 years ago, phone manufacturers began producing a display that Apple called the Retina display. I don't remember what Google called it because Google just ended up using the same terminology. The Retina display meant that our retinas could not see the individual pixels. Older displays, lower resolutions displays, like if you're using a 720p or 1080p monitor and you get like close enough to it, you can see the individual pixels, right, that make up the image. But most modern devices now, you look at them, it looks completely smooth. You can't see the individual little dots that make up this image because we are resolution limited with our eyeballs. What this question is going to ask is, how close do we have to get to be able to see these individual pixels on our device screens? So the 400 pixels per inch, that's what the industry uses to describe like what the display is doing, okay? This is like a pixel density, right? Okay. And so anything that's basically, I can't remember what it was, 360 something pixels per inch, anything higher than that, basically no human being can see the pixels. Okay? So generally, depending on the price of the display, they'll run this value higher, but really going past 400 there's no purpose to it. So I went and figured out how big an individual pixel is based on that pixel density. You don't have to worry about how to do that, okay? again, what we're going to do is we're going to find a distance. And we're going to do it by using the resolution limit, which is the operative one, y over L equals 1.22 lambda over d. Okay? And let's make sure we understand and know what the different parts of this equation are. Okay? So I like to draw kind of a picture. I draw it like up and down. But I've got two objects separated by a distance y. And those two objects are some distance L away from something that's looking at it. That's, by the way, the symbol we use in optics for like an eyeball. Okay? Could be the telescope, mirror, but in this case it's eyeball. Okay? So I tend to like lay out this picture just to orient myself. Okay? And let's see what they've told us. Okay? Do they tell us what y is? They do. Okay? What's y? Do you see? So there's lots of numbers in this thing. We got a number here, we got a number here, we got a number here, we got a number here. Which of these numbers corresponds to the distance between pixels? It's the 5 microns right there. Okay? So the 401 is kind of a red herring. This is kind of a red herring. What really mattered, right, was the distance from one pixel to the next. Okay? And so that means that our y is equal to 5 microns, or micrometers. And how are we going to write that? 5 times 10 to the minus 6 meters. We're going to convert everything to standard units to make sure we are hunky-dory. Do they tell us what L is? That's what we're looking for, right? We're finding the distance. How far away does the phone need to be from our faces for us to be able to see individual pixels? So our L is what we are looking for. So I'm going to say question mark, and I'm going to draw a box around it, or a bubble or something to remind myself that's what I'm looking for. I'm just going through this equation to see what I know, right? Do I know lambda? Yeah, what'd they say? There we go. And what am I going to do with the nano? 550 times 10 to the minus 9 meters. All right, do we know the diameter of the pupil? Sure do. 4 millimeters, or 4 times 10 to the minus 3 meters, right? Milli means 3, 10 to the minus 3? Yeah, okay. All right, looks like we got it all, right? So now we solve this equation for L. Plug and chug. Let's see. L, if I move L, I've got, let's do it this way. I've got y, and then I've got to put the 1.22 lambda down there because I'm going to swap it for L on the other side, and then I got to move d over. dy all over 1.22 lambda is equal to L. And now I can go ahead and start throwing in my numbers. D, 4 times 10 to the minus 3. Y, 5 times 10 to the minus 6, all over 1.22. Now, notice I'm not putting any units in now because I put in all standard units, and I'm solving for L. So what unit should this come out to be? Meters. 1.22 lambda, 550 times 10 to the minus 9. Yeah, I've definitely lost pages in my notes. Because I used to have these all worked out. Is it right here? Did I just put them in the wrong order? That's the next problem. Yeah, I don't have this problem. Anybody calculate it yet? What'd you get? 0.029. Is that right there? Yeah, that's it. Meters. Okay. So in other words, 3 centimeters. Okay. Which is about right. Okay. Meaning that we'd have to bring our cell phones in 3 centimeters away. That's basically my nose is longer than that, right? Okay. And get an extra. Now, can I focus on my cell phone screen if it's that close to my face? No, that's way within my near point, isn't it? Okay. So the practical application here is that no matter where I look at my phone, am I going to be able to resolve individual pixels? No. And so therefore, the display looks continuous, not broken up into little tiny chunks the way it actually is. Okay? So again, this is what we refer to in physics as resolution, right? Now in computer monitors, the resolution of the monitor is the number of pixels, the number of pixels sideways multiplied by the number of pixels down. They'll say things like 1080p or 4K or something like that, right? So 1080p means that I never get this right. It's 1080 pixels vertically and 1920 pixels horizontally. 1920 by 1080. Okay. I never remember what the other 4K. Well, 1440p is 1440 that and 2000 pixels sideways. It's like 2340 or something like that. I can never remember. Okay, and then 4K, right? It's 3000. It's numbers. I can never stand there. I gotta look numbers up. 4K resolution. 3,840 by 2,160 pixels. So 3,840 sideways and 2,160 pixels up and down, right? So again, if you go to your grandparents' house and they haven't upgraded to 4K yet and you're sitting in front of a 1080p, right, display, you'll be able, if you get close enough to it, you'll be able to see the pixels, right? But in a 4K, you have to get much closer to be able to see the pixels, right? That's why people will say 4K displays look sharper or whatever, right? Because you're not seeing the individual grainy parts that make up the picture. And if you're sitting at a normal distance away from a television, which is usually about minimum 5 feet, right? Depends on the size of the TV, but minimum 5 feet, you're not going to be seeing the difference in pixels anyway, even if it was a 1080p or standard definition display. Yeah?
Can you calculate what lens you would need to see
Yeah.
the pixels?
Absolutely. So, I paid Truman to ask that question. The picture on the left is a terrestrial or ground-based telescope's picture of Pluto back in the 1990s. Okay, and in this picture, we cannot tell the difference over here on the left between Pluto and its moon Charon, because this telescope is diffraction limited. Okay, the aperture is too small. The picture on the right is a Hubble Space Telescope picture. Now, the Hubble Space Telescope's got a pretty big aperture. It's like a 2.2, 2.3 meter tall aperture, round opening. Hubble Space Telescope is basically the size of a school bus. Okay, James Webb Space Telescope is bigger than that even. They had to launch that as like a piece of origami, and then when it finally got to where it needed to be, it had to unfold itself. Because to fit in a rocket, it had to be this big, but they wanted it to be this big when it was done, right? So they had some very clever engineering in there, which took all of its ideas from an ancient art form out of Japan, which I just love that. But anyway, the Hubble Space Telescope is able to resolve, because the atmosphere is not in the way and other diffraction limitations, able to tell the difference between Pluto and its moon, Charon. Okay, so, and that's how we say that word. We're not sure really how the Greeks said it. Ancient Greeks said it. We know how modern Greeks say it. This is a picture of Pluto from the New Horizons spacecraft, okay, that flew by Pluto about, 8 years ago, 10 years ago, and got within a distance, I think it was like 400 or 500 kilometers, like 300 miles from the surface of Pluto. I might be wrong on that number, but it got close, right? And here, that spacecraft was able to resolve features on the surface of Pluto that we can't possibly see with James Webb or the Hubble Space Telescope. Again, because of diffraction limitations. Closer is better, right? And the diameter on the New Horizons camera was like probably only that big, right? But because it was so much closer, it was able to see these things, right? And Pluto turned out to be a place of color. What you're seeing, the white here, is solid carbon dioxide and nitrogen gas that's been sublimated. It's so cold there that it goes beyond its liquid into its solid forms. So think of like glaciers made of nothing but solid nitrogen, right? Flowing on the surface of this world. It's just absolutely incredible, right? We live in such a cool age. If you go into Google Maps or Apple Maps or any of the others that have satellite imagery on them, and we use the term satellite very loosely because a lot of the imagery you see on Google Maps is aircraft imagery, high-flying aircraft. You can actually go on like FlightAware and look at the tracks for aircraft that are flying today. And if you look at it long enough, you can figure out which ones are the imaging aircraft. They're just flying in straight lines. They're not going between airports. They're just kind of doing these straight lines over places, right? So they'll fly over Fresno like once every 3 or 4 years to kind of get an update on the imagery, right? So most of it nowadays isn't satellite. Most of it is airplanes. But anyway, you can tell the difference here in resolution from different quality cameras and things that they use. This is a bit of an older picture, but Google Maps used to tell you the resolution of the imagery it was using. This is 30 meters per pixel, meaning that a pixel on the screen can distinguish between objects that are 30 meters apart, right? 10 meters per pixel means that for every pixel of the image, it can resolve objects that are 10 meters apart, right? Nowadays, you go onto Google Maps and you can get down to centimeters per pixel. I think like there's certain areas, like for whatever reason, the Las Vegas Strip and all that kind of stuff is down to like 10 centimeters per pixel, 15 centimeters per pixel. So on the day that they took the pictures, you can see individual people. You can distinguish individual people walking down the strip. You can certainly tell the difference between cars because cars are much bigger than centimeters and so on and so forth. So like the resolution of the data, right, helps to inform what you see and what you can't see, okay? And by the way, did they catch 2 of the people that stole stuff from the Louvre? Did you guys hear about that? There was a heist at the Louvre, 9 o'clock in the morning. People broke in, stole hundreds of millions of dollars of jewelry, right? And then it took them 7 minutes, right? And I think they arrested 2 people over the weekend in conjunction with the theft. Anyway, I only remember that because of the Louvre Museum. So let's do a calculation. We're gonna do some what ifs, okay? And the what if here is, what if we take the Hubble Space Telescope and instead of pointing it away from Earth, we turn it around and we start looking at Earth, right? Now, our calculations is not going to take into account atmospheric variation. There's lots of things that can make these pictures harder to deal with. But there are technologies, adaptive optics and other things that can correct for all the distortions in the atmosphere. But we're just going to do main simple thing. And I can't think of a reason why any government, person, would want to point something the size of the Hubble Space Telescope down, right, to see what's going on the surface of the planet anywhere at any time. What I will tell you is that the National Reconnaissance Office, the NRO, which is responsible for satellites and satellite imagery for defense and intelligence purposes in the United States, they launch a new satellite every 18 months or so, 12 to 18 months, okay? These are classified launches. They have to publish the launch date because they have to tell pilots to not go anywhere near the launch area for safety reasons. and there are enthusiasts, I am not among them, but I do like reading their reports, who will track the launches and watch the angle that the launch is taking and get a good idea for the orbits that these satellites are being put in. Each one of these satellites is the size of the Hubble Space Telescope. They are basically like school bus sized satellites, right? And they go into orbits that are very close to the Hubble Space Telescope orbit and pretty darn sure that they're pointed down, right? Although I don't like mentioning his name in class, I will this one time because he screwed up big time. President Trump in his first term actually leaked. He tweeted a picture of I think it was an Iranian missile complex. And he, of course, was bragging and being really stupid, but he tweeted this picture, and all of us that sort of follow spy satellites and like their capabilities nowadays and all that kind of stuff, all of our calculations were verified by that one tweet. Because it was an unredacted, like literally, they had given him a picture and he's like, oh, right, and tweeted it. And the resolution of that picture was insane. And like, we could almost like tell you which satellite it came from, right? Like it was, so the calculation we're about to do has been verified. Just say that. Okay. By the government's most egregious leaker. Okay, so what do we got? We've got, okay, I like my picture. I draw two dots to show the separation between objects, and then I've got like my distance away, where in this case, a telescope is pointed at what we're looking. Okay, and that's by the way is an L. I don't know why I put my L there. L, right? That distance there. Okay, so do we, numbers. They gave me 613 kilometers. What is that? That's L. 613 times 10 to the 3 meters. Okay, they gave me the diameter, 2.4 meters. Don't have to, yeah, I remember pretty good. I said 2.2 or 2.3. It's 2.4. Good. Wavelength, they gave me 550 nanometers, so times 10 to the negative 9 meters. And what is the minimum separation that the Hubble Space Telescope can see? So what are we solving for? We're solving for y, right? We're looking for that separation between objects. So what is that? Y over L equals 1.22 lambda over D. And we've got, is that 1.2, no, solve algebra first, Mr. Balogh. Okay. So y is going to be 1.22 lambda times L all over D. 1.22, 550 times 10 to the minus 9, and 613 times 10 to the 3, all divided by 2.4. Because I put everything in meters, I should get meters out. And I did this one. I got 17 centimeters, 0.17 meters for y. So Hubble Space Telescope, which is, by the way, like 33-year-old technology now, can resolve objects, see the difference between two things that are 17 centimeters apart. So can the Hubble Space Telescope tell the difference between two people that are standing next to each other? Yeah. Right? Normally people stand when they're talking to each other, they stand about this far apart, right? It wouldn't be able to resolve, say, two people hugging each other, right? Because that's closer than 17 centimeters. Can the Hubble Space Telescope read license plates? Are the characters on a license plate more than 17 centimeters apart? 17 centimeters is about that big. No, we could fit like 3 characters right in there. So the Hubble Space Telescope can't read license plates. President Trump showed us that there are devices that can. Okay, right? That we're basically getting to a resolution limit where we can almost read license plates and tell the rank of the guard that's sitting at the guard station, right? Like it's that good, okay? Which means that the satellites that the NRO is launching is much more capable than the ones that the astronomers get to use for looking at the universe. I'll leave you with a famous picture that is the moral of the story when it comes to resolution. This was a picture that was taken of Mars back in the 1960s by one of the Viking orbiters. And there is a very famous part of this picture that sent okay, I'll be nice today, that sent all of the conspiracy theorists into a frenzy. Can you guys see it? See it? Oh, let me zoom in on that section of the picture for you. Okay. Right? What do you see? Martians. The aliens are on Mars, right? This face on Mars. This sent, oh my gosh. You just sent people. And to this day, I still get emails from conspiracy theorists, who are like, look, we found evidence. Okay, this is in the 60s, okay? I wasn't even born when this happened, but I still get tortured by it, okay? Right? So there's the original picture. There's the zoomed in portion, taken by an orbiter that had a resolution of like kilometers per pixel. And if there's one thing the human brain is really good at, like we are programmed to be able to do, see faces. See faces in anything, right? So it's no doubt that if you get something that looks even vaguely like a face, people are going to say it's a face. And the Egyptians built their pyramids and whatever. I don't know. I've heard it all. Okay? So here's the same thing taken by the Mars Reconnaissance Orbiter in the early 2000s. It's exactly the same place on the surface of Mars. No, it's not. You scientists are hiding the truth. Whatever. Here's the data. Okay? The face is a sand dune. It's just with that lower resolution, the optics couldn't see the detail, right? And again, because of the sun angle and all the kind, it made it look like a face, right? It's not a face. It's a bacterium. Realizing that this is like several kilometers long, right? Like this dwarfs a sand dune in the Sahara Desert, right? Like this is so much bigger, right, than any one of those. So I'm sorry. There just aren't any Martians on Mars yet. Although, 3 weeks ago, did you hear? We detected the possible biosignature in the Curiosity data. Which rover was it? It's either Curiosity or Perseverance. It was probably Perseverance, right? But they found chemical signature that 99% sure comes from a biological source. So they're now trying to figure out if it's contamination or not. The government shutdown kind of stopped all information coming out of NASA. So just waiting for the government shutdown to end, and maybe we'll get more information about that. So life more than likely happened on Mars. Just not the kind you're thinking of. Little bacterias. All right. That was the end of this unit. You can stay, work on your homework, get help, all that kind of stuff. You can leave. Whatever you decide to do it safely. And I will see you tomorrow. What are we doing tomorrow? We're reviewing.